Okay, so here we will. I reused an OpenPower view of the fact that this view is really aimed at showing you that we want you to have the feeling that OpenPower-based machines are aimed at facilitating the streaming of the data from one port to another. It's a one port to another. It's really the main goal. So today we will go and discuss how CAPI and OpenCAPI is not just adding an FPGA driven by an application. So it's usually what people have in mind. Even worse, they say OpenCAPI is just a new fast link, which is true, but it's not what we will see in a minute.
You just excuse me, I'll just make an
Please.
announcement. Sorry, I think those who are going for the 4 o'clock facilities tour, carry this phone inside, and it will be ready. I think some of you, right? Yeah, okay. So please go to the main desk and then carry it. Okay, sorry.
No, it's okay. It's okay. It's like in a family, you have to deal with.
Too many events are taking.
Exactly.
Could you just grab the connector from here?
Which connector you are looking for?
Here.
You missed something.
Yeah, please.
Okay.
Okay, good. You're welcome. So the main thing that we like to tell is a good story that my colleague, who is a friend actually, he hired me two years ago, and he said, please come, I have a huge amount of work. It's very funny, and I need help. So I was one of the remaining hardware engineers in the company, and I said, oh my God, that seems very complex to me. And he said, no, come. In 11 days, I've been able to accelerate by 35 a very basic computation stuff that people would have thought it would take months. So I said, okay, tell me your story. And this story was so funny that we decided that we could tell this story to you. The fact that this story is happening, it is now 2 years or 2.5 years ago, is the same story that we have regularly, because people have in mind that FPGA is a nightmare, is a hell to program. And this was the fact, until we had this tremendous effort that Xilinx-like manufacturers have made to render FPGA technology accessible to software engineers. So, what has it done? We'll see in first part what is an FPGA, what is because most of you, I guess, are coming from the software world. Is that the case? Are some of you hardware guys? One? Okay, one. Thank you, my colleague, my friend. Please help me. Okay, so the goal is to address software engineers and to make them, at the end of the presentation, not being afraid of searching and programming an FPGA. The part 2, we'll see how, with several contributions, not only IBM, it's been possible to make a very simple example in few hours coded into an FPGA. So we'll see different words like what is CAPI and OpenCAPI mainly in this presentation. So let's have an example. An FPGA is a piece of hardware. It's a component that you buy from a company, for example, Xilinx, or previously Altera, which is now part of Intel. They will sell you a chip, usually at a good cost. They know what you can do with it. And they will provide to you an almost finished chip. That is, they have made the complete construction of question. Oh, sorry. They have made the complete construction, but they did not hook up the different locations. So you have piece of, we call that LUT, logical unit. And these are small items that contains the basics to do some electronics job, digital job. Additioner, registers, handling a clock, and so on. So I don't want you to enter into these details, but you have the minimum hardware duplicated many, many times and not interconnected. They leave to you the fact that you will interconnect the hardware logic the way you want to build your function. Okay? So it's really a sea of register gates, piece of memory, ready to be wired, and they just forgot the last step of the chip construction. Okay? It's up to you to make the construction you want. You can duplicate the construction. Yeah, I tried, but it didn't work. I plugged it, but it didn't work. I don't know why. Oh, you know what? Oh, okay, it's working? Good. Very good, the pointer. Excellent, excellent, thank you. Whoa. That's a haunted house. So it's up to you. You can duplicate exactly the same function. For example, say you want to uncompress a video, and uncompressing in hardware is much faster than uncompressing in software. So say you have 3 video uncompressor, you can duplicate 3 times the same function. So you pick up some blocks, and the system will build a video H264, 264, and PEG4 uncompressor. You can have 3 of them. If you have enough room in your FPGA, you buy a bigger FPGA because you want 3 uncompressors. You can have 1 uncompressor for 264 and 1 for 265, for example, a different one with the different constructions. What you need at the end is be able to communicate with your server. So initially IBM for CAPI 1 and 2, and now OpenCAPI will provide to you what I will call regularly the blue box. The blue box being a transportation box whose name depends on the technology. It used to be named PSL for CAPI 1. It's now a little bit different for OpenCAPI, but the goal is the same: be able to exchange packets between your hardware and through a fast link. This is why OpenCAPI is not only the fast link. There is a fast link here, but there is also some logic here that is provided to you, and there is some logic existing under the P9, we will see, to allow you to seamlessly exchange data with your hardware. Okay? So we will be speaking about building this. We will be speaking about how things are exchanged and how we have made stuff very easy for you to use. And we'll go through 4 blocks that we need to make this available to you. Have you any questions here? Okay. How many of you have knowledge of what an FPGA is? Okay. Oh, that's half of you. Okay. Good. Deep knowledge of what an FPGA is? Okay, pretty much. One. Okay. And the rest is a good idea of what is an FPGA. So 3 cases. Sorry for the sound. 3 cases where you would appreciate to have an FPGA working, or an external accelerator. An external accelerator could be could be a GPU or could be an FPGA. So let's call that an accelerator. You would like to use an accelerator because you would like to boost a function, a specific function. You would like to have something that is particularly tuned, like we spoke about uncompressing a video. You want to have a very fast uncompressor to get very, very fast bandwidth, because you are a company providing video on the web, and you are treating video all day, and anything that could increase your capability to fasten a compression or decompression of video would be useful for you. You would like to offload your CPU. You can do many things in CPU, but your CPU is overloaded. 100% workload is completely destroyed, like Lucky Luke, Jolly Jumper horse. When Lucky Luke jumps on it, the horse is like this. So you would like to offload your CPU. There is a need for you to find a solution because of more slow. You cannot handle next generation. You know that your CPU will be dead. Or you can also need accelerators to free network resources. For example, you are a security company and you collect, like Vinci does in France, you collect from tunnels, you collect hundreds of video from cars running into a tunnel or from parking lots, and you don't want all this video to be uncompressed by your CPU, because most of them, they are useless. During the night, most of the video, nothing happens, nobody parks, nobody is in the tunnel. So you would appreciate to have an external acceleration solution that uncompresses this video, checks if there is any image movement or change, and if there is no change, then you can safely decide that you throw away the video. And in this case, you would simply kill the huge number of data that comes into your system, you reduce it and you avoid penalizing the CPU processes to do useless job that you have determined that is not worth to be done. Okay? So you have two options today. Most options are, you can go around, but most options are running around GPU, which, as we know, were used for gaming initially, and then we realized that this gaming computation could be reused for the intensive computation that we had in the industry. So the clever GPU providers said, hey, I could make a lot of money instead of playing with teenagers and have a very niche market. I could make a lot of money, and they are doing a lot of money with parallel computing, and that we know, you know, obviously, because you're here. Another option is using an FPGA. So we said that providers you could buy from providers a chip, and you could find also providers that make boards that will offer you a complete dummy C of logic, C of gate, that you could assemble by yourself. But we will see assembly was not that easy, so we'll see how we do it. The good advantage of that is that it's very low latency, it's very fast, and it's very predictable. You know exactly how much time will be required by the hardware to do a function. And usually it's smaller system and it consumes much less energy than high energy demanding GPUs. So one is, let's say, fast, the other one is really real time. You input data, you wait for three clock ticks, click, 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 and then you get your data out. It's very, very, very impressive. There are several acceleration paradigms that we have talked a little bit earlier. The first is you want to make modifications on data that your server is owning. You don't want to talk to the outside world. You go into an action that you set up into your FPGA, FPGA being the green block here. So it's mainly, let's say, your board, but mainly your component that you have programmed to do a function. And it has a local memory eventually, but it is exchanging data with the CPU to make a calculation. The calculation we mentioned in the good story was a SHA3 calculation, so it's very basically calculating keys, and for this you just need to get some parameters from the CPU. So the exchange is very simple. You compute the keys and you return the keys result to the CPU, or you compute a matching to the CPU. Matching is okay, matching is not okay. Like, for example, a brute force password recovery, you just give the instructions to the calculator. You have the calculation completely done here, so very little number of data exchanged. It's just computation only, and once the computation is successful, you say okay, or you say no, I didn't find. Okay? We could also mention that because you have an FPGA, because you have a board, you can have external connections, and that's very interesting because you can hook up memory, as we said. You can hook up a local memory into your board, but you can also hook up Ethernet. You can also hook up storage, whatever type of storage you want, NVMe or any coming SCM or anything. So your board is made and plugged into your server, but offers you a connection to the outside world, which your GPU cannot offer. So we'll use that for anything that is compressing input or output data. An example could be, for example, for security. You would like to have a very high security, and you don't want your human resource department to flow anything out on the internet. You absolutely don't want them to provide anything on the net. You want them to be on the side. Any IP address coming from the human resource department, I say that because I'm an engineer, so I'm not working in human resource department, but they could tell the same about us. It's a funny thing that, so you can exactly, in the FPGA, you could have the NIC function be performed, and you could manually, mechanically, I would say almost mechanically, electronically check with registers that you have programmed yourself, the header and the type of header. If the header comes from this department, you say no, this is not correct, and you raise an alarm. You can raise an alarm locally. that is handled manually, for example, or you can come back to the system if you want. But you can handle everything here outside of the operating system. So you can really filter packets on header content, on content. You can put a specific bit in your packet that you want to send to somebody, and if this bit is not here, or if this bit is not correct, or this CRC is not correct, somebody has manipulated the packet. And you can control that on hardware completely outside of the OS. So this is very, very huge. The things you can do in terms of security with an FPGA. So anything concerning cryptography or security is very interesting. I will mention later on the HFT. We'll come back on that later. So we have put here a few slides to give you examples of what we have seen in the last years. We talk about MPEG-4 or coming generations of video encoding, decoding. We have, so on Coral, this big machine, they have run benchmark Coral type systems, regular expression matching. So FPGA are very good at that because they are very fast to check on a huge library of words if they can match an expression, because it's really simple registers, and once you get the expression matching, then the bit trace instantaneously. There is no code running, it's just a few ticks of clock running, and you get your information. Inline compression of data. Another set of examples here. Inference of face recognition, so artificial intelligence inference in an FPGA. Smart surveillance of fault detection. This was mainly an edge function that was programmed. I don't remember which, deep neural network acceleration. Oh, that's an implementation of NVDLA on an FPGA, and I can barely read this one. But mainly we can sort out in different domains, video domains where video are really computation demanding functions related mainly to compression and uncompression. Banking and finance, so this is where the HFT, high frequency trading, these guys are just crazy, and they want to have us faster into the wall, so they want to have very fast instructions going or coming out from the what do we call the bourse, stock market, make decisions and return orders very quickly. So latency for them is a key point. Algorithm acceleration. In this case, we don't need. We might not need network connections. All that we spoke about encryption. I talked a word a little bit before. I said a word on that. And machine learning, deep learning. The inference is really perceived as being something that FPGA might be more and more used at. Probably not on the machine learning side, but once the computation factors, the computation coefficients are known, it's a question of loading tables. So there, it's very interesting to see how power systems can handle very quick exchange between the memory and the FPGA, and then inferring the model and return the results. So FPGA might have a good future in this area, and there are very interesting things going on here. So let's have a look into the details of why we would like to use OpenCAPI and what it brings to you, because we said it's not only a fast link, so let's go into more details. Let's say we have a huge table of 1 terabyte that is located outside your server. So here is your server with your local processor and your local memory, and you have a table which is not in your memory, that is outside, and you would like to compare it to another table, okay, that is located into external disk. It's something that you have to do, and this is a task that requires you to get you want to get the common element in between these two huge tables. So one classic approach would be to use your card, your network card. You hook up to the network. You get, so we'll introduce you 2 words that we will use in the presentation. You have a main application, which is the overall application that runs from the morning. You launch the application, and you have the comparison function. The comparison function is a function that you have detected to be the one that you would like someday to be accelerated. you cannot accelerate everything. So you have to define what subsection of your main software is a good candidate for acceleration. The same in GPU, you do not accelerate the complete application. So let's say your combination of your application and your comparison function will grab from the network through the NIC card into the server memory all the table. So you have a direct access to the host memory because you are in the CPU, and but you have to ingest. And we made a very basic calculation here to ingest 1 terabyte through a very huge computation network card. It would take you 20 seconds. So the question is, where are your data? Your data being outside, you need time to get them into your local CPU. Okay? Now you introduce an FPGA to do the function that will compare the table. So you take your initial configuration and you say, okay, now I will use an FPGA. I will put my function inside the FPGA by a good manner that will enter in the details later on. I will tell you how to do that. So you have defined that the comparison table can be done in hardware. And you have a good mean to do that. We will see that. So let's say you have obtained this programmed FPGA. He can access to the network because he has his connection. The NIC can be done into the FPGA, or the NIC can be outside the FPGA if you want to save resources from your FPGA. Instead of consuming hardware to build your NIC, you put a card having a NIC and an FPGA to save the FPGA resources for your application. But if you want to have control on your NIC, you can put your NIC into your FPGA, as we said before, because you want to check the human resource headers and so on. Okay? So now the function is offloaded. Very good. The CPU is quiet. The server can be accessed by the FPGA, so then you free the network resource of your local server card, which will not be used for this application. And you think now that you will save memory savings because you can get all the memory inside the FPGA memory. So you will grab all this local table to your server here, and you will grab this here, and you will make the comparison here. The problem we have here is that we need a software driver. The CPU is used to collect the data from the server and bring them to the FPGA. So this adds a level of complexity because the CPU has something to do to transfer the data because of the software driver. And you lose the direct access to the host memory if you are making the comparison and in the same time another application is modifying the data. By the time you compare the data has changed and you're dead, or you make a mistake. The FPGA is completely slave. It waits for the CPU to tell him, okay, here I provide you new data, here, wait, listen, I'm providing you new data. Data are pushed to the FPGA. You utilize a huge bandwidth in your PCI Express because your card is plugged to the PCI Express bus, and you lose coherency. As we said, somebody modified the data here, it's not modified here. You can only have one user, one application, and one function. So now, what happens if we put a CAPI or OpenCAPI enabled card? The CAPI card will have a different connection to the CPU. In the CPU, we will include, and this is true from Power 8 and coming generation, Power 9 existing today, Power 9 Prime, Power 10, whatever. And in the ISA, I think it's related to that because ISA is also related to OpenCAPI. You have a specific piece of hardware here, which is not your core. It's not your microcontroller. It's a specific piece of hardware that will play the role of the software driver and treats the conversion of address for you. So function is again offloaded, as we said earlier, accelerated. The server networks are saved as before, server savings as before, but because of the CAP, which is a CAPI hardware driver, you do not require CPU instructions to run a software driver. That means that the FPGA will act as a master and say, I've made the comparison on the beginning of the table. Now I've checked all the A letters. Now I'm going to the dictionary. Let's grab all the B words, B beginning words. So it will by itself talk to the CAP and grab into the memory the B section of the dictionary to make the next comparison on all B words and find if the B words from this dictionary are also the same, are here, and if they are common words, then it will store them in its local memory. For example, it's an example. In this case, you have completely freed the CPU. The function accesses only when data are required. So your function is completely in autonomous mode. You don't need the C word for the moment. Don't grab them. You will grab them when required. Okay? And it's really an output of your function inside the FPGA. You have a full coherency of data because when you grab the B words, you grab exactly the one that are here. Okay? And you don't need to grab the C words before you need them. So the data that you get for comparison are exactly the one that are in memory. There is no local copy. Okay? You grab a data, first B word, compare, okay, not okay, throw away. Next B word. And as soon as you get the data, you do not duplicate. You get the data, make the comparison, and throw away. You do not take all the A words in your memory and make the comparison. You take the first one, the second one, the third one, and as soon as you get them in stream mode, you make the comparison and check common element, not common element. Throw away, sort, throw away, sort. Okay? So no duplication of data. That's very important. And most of the time, many people miss this point, which is very important because in CAPI, the C stands for coherency. Okay? And this is one keyword. So, sorry. Coherency of data, as we said. No need for address translation. The CAP is dealing that. So when you program your application, you say, your application say, hey, this function, grab all the dictionary from address 100. This guy, when you program it, he will get the address 100. So you will just need to provide to him address 100 and nothing to do, no manipulation of address. He says, hey, give me address 100 content. And this guy will make the conversion to get the physical location of address 100 virtual address content. Okay? That's very important. It's very, very, very easy to program. Multiple thread, multiple users can be associated to multiple actions. We did not get the need for that, so in CAPI 1 and CAPI 2, we have only addressed one user, one function for the moment. In OpenCAPI, everything has been reorganized, and we should have another way to address that, but we have not had demands for that for the moment. Okay? So, using CAPI and CAP driver, you get very small latency because you are very fast to get the data, very high bandwidth because we reuse the PCI Express in a different mode, not paying the overhead of PCI Express. So we just use PCI Express for the card recognition. When the server boots, it checks, it interrogates the FPGA. If a specific register says, hey, I am an FPGA, I'm from this company, and I'm CAPI, the kernel will say, okay, let's get rid of PCI Express connection. Let's get rid of the software driver. I hook up you to the CAP. Whenever you have something to ask me, please ask me the address. I will provide the content to you. Okay? In read and write mode. You are master now, and the kernel treats the CAPI card specifically. The kernel, the official kernel, are supporting CAPI 1, CAPI 2 mode in P8, P9, and coming kernels will be supporting OpenCAPI. I think that the latest kernel for P9 is supporting OpenCAPI. Yes, I think so already. But by the end of the year, this will be completely official. So, very high bandwidth. Programming the FPGA can be done using, we'll see that later. Power simulation model, we'll see that later. So all that comes with the fact that you have selected the CAPI stuff. Open source, we'll check that later. And you don't depend on a card manufacturer, provided that you get a Xilinx part inside the board. You can pick a board from Alpha Data, Bitware, or now they are Molex company, but Bitware and Nalatech, all different companies making cards. You can make your card yourself into your lab, into your university. Just grab a Xilinx component because everything is mainly working with Xilinx. Initially, we made first experiments in P8 with Altera, but since Altera has been acquired by Intel, it's easier for us to work with Xilinx for the first reason. And second reason, the Xilinx IOs are like ours, very good. So it's a very good partnership we have together. We have very fast I/O, it's facing very fast I/O. That makes the links working very nicely.
So you're saying that if I've got an existing PCI Express FPGA card, it will work with this my motherboard supports it?
So the question, your first name is? Nick. Nick's question is, I do have an FPGA board PCI Express in my lab. If I plug it into a power server, will it work? So if it's a Xilinx component, there is chance it works. If it's an old Xilinx component, it will probably work in CAPI 1 mode in P8 servers. If it's generation Vertex Plus, that is the I/O is faster, you might have the chance it will work on a Power 9 in CAPI 2 mode. Okay, it will be recognized as a PCI Express at the beginning for the recognition, for the registering. But as soon as you have programmed your FPGA with a CAPI code, with a CAPI binary, then the specific register will say to the kernel, I am a CAPI card. Then the kernel will switch forever until reboot into CAPI mode, and then you can use your card in CAPI 2 mode with the bandwidth we will see in a moment.
And from what I understand, the big benefit I'm going to get is my host memory is in my address range and my kernel's on the FPGA without having to go through the kernel.
Yes, yes, we'll see that in details.
Yeah.
So huge benefit. And if you're lucky, you don't have to buy a new card. We just need to check what component you have on your card. And if you are very lucky, the same component has already been integrated into the open source framework that we will provide. We'll talk in a minute. And if you are really lucky, you have nothing to do to play with it. But you need to be twice lucky. You might be. Okay, let's go now into, I'm sorry for software people, I will talk a little bit of hardware. And you will see my eyes will go like this because I come from a hardware world. But I think it's interesting in terms of overall knowledge, and this is why I'm here today. And you're welcome to ask me questions later on. Keep in contact if you need. The third generation is great because it was introduced, I think it was 2016 or 2017. And we actually made the proof of concept in the P8 generation. And to be frank, we had many rich feedback that the bandwidth was not enough to offer to interest people to invest in the technology. So it was mainly used for us for tutorial purposes. We have built lots of courses. We have made experience ourselves on this technology that IBM was providing. And now it's mature enough since late 17 on P9. The CAPI 2 generation is available. It's a mature technology now. And on P9 CAPI 2, we are running over PCI Express Gen 4 links at a theoretical complete raw bandwidth 16 bits per second on 8 lanes, which makes a theoretical 60 gigabytes per second capability. And out of this, we can get as high as 14 gigabytes per second useful data, useful payload capability. The estimation, total latency, it's always difficult to speak about latency because it really depends on how you make your round trip and how you set up things and on the overload of the machine in general and so on. But it's in the order of alpha microseconds to make a back and forth of data from the FPGA to the memory and back to the FPGA. Okay? So using this link CAPI 2, you hook up to a Power 9 server having its own memory attached. So this is a scale, I never remember, scale out and scale up server. One is high end, one is low end. You are English, so you should tell me. The low end is scale out or scale up? Scale up for low end? Why is it low and up? That's strange to me. Anyway. And on the same P9, you might have different links that are OpenCAPI capable. It used to be CAPI 3, but since it has been opened in the OpenCAPI consortium, and until yesterday you had to be member of the CAPI consortium to get the information. As university, you are, I think there is a free membership to OpenCAPI consortium, so I encourage you or your teacher or you're responsible to consider that. On P9, some links can be OpenCAPI capable. In this case, we get rid of the PCI Express limitations because we have much faster links that PCI Express 4 doesn't offer. So we use 25 gigabits per second on 8 lanes, which offer 25 gigabytes per second capability, out of which we can get as much as 21, 22 gigabytes per second measured. Okay? The latency being drastically reduced again. All right? So, OpenCAPI. We spoke about this open power. It's somewhat related because many companies participated here, almost the same company as open power companies. I don't like much this chart because it's not always easy to understand what we can get out from it, but basically what we want to know is just because you have this P9 in the middle, and because of OpenCAPI capability, you can look up different solutions as like acceleration, current memory network controller. Mellanox is a candidate for that. Advanced memory controllers and storage. I can barely. Coherent storage controllers. Okay, to get connection with hard disk and standard memory. So what we want to say here is that OpenCAPI is providing, because of the C, coherency acceleration, it provides a way to hook up accelerators, whether they be FPGA or specific ASICs, like Mellanox has a specific ASIC that has been produced to be using this CAPI technology, so it can exchange data with a CAP driver, okay? And specific hardware that you can hook up to get these very fast links and fast coherency access to the memory. So some can be accessible through CAPI 2 over PCI Express Gen 4, as we said. Some can be accessed with OpenCAPI 3 and coming generation 4. And standard memory will have a specific version of OpenCAPI 3, which will be named OpenCAPI 3.1. It might be a little bit confusing, but 3.1 being a tuned version of CAPI specifically dedicated for standard class memories, okay, to have a very low latency, and it's really aimed at being hooked up to memory. So the main CAPI we speak about today is CAPI 1 and 2, eventually CAPI 1 for training purpose, CAPI 2 for easy access with existing boards, no pain, plug the board, it works, and eventually very advanced and very fast solutions using OpenCAPI specific hardware. Okay? Does it make sense to you? All right? I know it's hardware, so it's not always easy to share with you, but okay. Please interrupt me if you have any question. So I don't think we need to go very in details in this very interesting slide, although it's interesting, but mainly what we want to see is a different generation. CAPI 1 is only for P8, and as I said to Nick, is really concerning old FPGA which do not have the latest fast links, okay? Virtex Plus FPGA will be concerned by CAPI 2 and OpenCAPI, or let's say CAPI 3, okay, technology, to increase the bandwidth. Over PCI Express 4, we can have 16 gigabytes per second because we have 8 lines, 16 gigabit. Or we can have 25 gigabytes with the same 8 lines, but at much faster rate on specific hardware here. We get rid of the PCI Express. Just we need the PCI Express to get the power supply because it's easier to plug the card into a PCI Express slot, but we will not use any pin but the power supply. Every exchange will be done by OpenCAPI. Okay? Okay, this is the different organization. I don't think it's worth to go into these details today of how we have hooked up the different fast lanes of our P9 scale-up and scale-out versions here. So this is why I said in the Raptor you will get the scale-up version of the P9. Don't laugh, huh?
Raptor would be the scale-out.
Scale-out?
Right? Yes.
Oh. That means
Scale-out is the one that goes up to 192 cores in a single machine.
okay, you're much easy on this to talk. Okay, if you have any question, ask Mark. Okay, good. So this is a different way that we can organize a system based on the power. So it's really important to understand that from the power choice, you decline different systems architectures. And at the end, for you as a user, you might have different numbers of CAPI2 capable ports or CAPI2 PCI Express ports that are PCI Express ports that are CAPI2 or not capable, and you can end up with different connectors or not if they are hooked up to the fast links of the power. Okay, the same fast link can be used for NVLink or OpenCAPI, but the protocol is a little bit different. So when you build your system, when the Open Power manufacturer builds his system, he makes his own choice how he will dedicate the pinout of the component to which connectors he wants. Okay, so this is going into the source of how at the end you get so many CAPI2 capable ports or OpenCAPI capable port on your chosen machine. This slide begins to be a little bit old, like it's 1 year old, but it's comparing the total round trip on different Altera Intel, now Intel machines, or Intel x86 machines with Altera, at this time it was Altera Stratix 5 FPGAs. See how long it took to make a round trip, okay? The good news is that with PCI Gen 4 P9, that is equivalent to CAPI2, we had a round trip here in this order of magnitude, where here we are less than 300. So again, it's very difficult to discuss about these figures because these are commercial figures. The trend is to say that from CAPI2 to OpenCAPI, there is not only an increase in terms of bandwidth, but it's very important also that you can account on a severe, important increase in terms of latency, time required to get access to your data. Okay? So that's the total latency here that we have. Adding, theoretically, this phi, I don't want to go into the detail of that because this is purely the link latency that you cannot reduce. But thanks to very good Power 9 capability of IOs, and thanks to very good, excellent capability of Xilinx, the FPGA provider we work closely with, we can achieve a very low physical, unavoidable latency on the link. And this is what you have to remember. Okay, I won't go too much in details in this OpenCAPI 3.1 and 4.0 evolutions because I think it's more important to concentrate on the CAPI stuff. Something very interesting for you, and this discussion we had with this gentleman whose name is Jim. We probably want to have further talk on that, but based on the Power 9 system, having its memory access here, we can forecast different hooking up. So we can put, for example, a board, an Alatec board, which has a 2 terabyte NVMe inside the board. So it's a two sub board that we plug here, which offers through OpenCAPI an access to an external disk. We can hook up on the same board, remove these parts, and plug external drives. Okay. We can also plug FPGA, which are more network oriented, okay, offering good network capability. All these can be hooked up with CAPI2. on a machine. On the same machine, this is the AC922 in its air-cooled version, in which you can only have 2 GPUs per CPU, where on the Summit machine, the top 500 machine, they had water-cooled, and they could afford to have 3 GPU per CPU, 6 GPU per node, in our case 4 maximum GPU per node. The specificity and the point of this machine that when you want an OpenCAPI link, you will remove 1 GPU and get the hard links from the GPU and use them as OpenCAPI. So you have to remove 1 GPU. We have not enough fast link to address 4 GPU plus OpenCAPI boards. Okay. So in the AC922 machine, we have 2 Power 9 processors. The first one can be hooked up to a CAPI 3 25 gigabyte link connection, and the second one can be hooked up to 2 GPUs in the air-cooled version, as I said, and we have put for you all the main bandwidth capability to let you consider how fast data can move from here to here, back and forth, or from here to here, back and forth, or from here to here, back and forth. We'll see an example. So let's see 3 use cases in details, in a very high level details. For the internal history, we have 2 support teams. One is in Europe, my team with my colleague Bruno, and the team of our colleague Lu Yong in China, addressing Asia, where Bruno and I were addressing Europe and America customers. So the China team, we have good relationship with Lu Yong, so I'll tell you some good story here. She came to Bruno, and Bruno is my colleague. He hired me and he said, I have introduced this way to program FPGA, program with C and not anymore in HDL language. We'll see this in a minute. And Lu Yong called Bruno and said, oh, I tried with HLS, so this is the way of coding FPGA with C, but the results are awful, I cannot get rid of that, it's a disaster. So we decided to go back to VHDL because we know that, and we'll spend as many weeks as required to code the scatter gather example I will show you in HDL. Now this is the story beginning. Bruno is called by our colleague and says, please Bruno, you are a specialist of HLS coding, can you tell me what's wrong? In the meantime, we go to VHDL. We have been to VHDL, and VHDL's results are much better than HLS. So Bruno came to the HLS side, and I will tell you the end of the story later on. So we want to gather memory data. Okay, a Chinese customer, wanted to collect a huge number of data located in the host memory and grab them, but the data were spread at different locations. Part of it was here, so like the A side of the dictionary was here, the B side was the other way, the C side was here, and there were blanks in the middle, okay? So it was really gathering different scattered piece of memory. The thing is that how can CAPI be helpful for that? So the first thing that we can consider is the traditional way. The CPU is collecting all the pieces of memory and putting them into the FPGA for treatment. The other way is the FPGA is collecting each part of the memory and collects directly here. So we'll see the difference. We have an example with 2 megabytes of data spread into the FPGA. And the spreading factor is the following. We can have 64, we have 1,000 blocks of 2K, 2,000 bytes spread, okay? And there is a table which stores the exact locations of each block, okay? This was to have an example to work with, all right? So we will work on the traditional way on this side and CAPI way on this side. Traditional way, we want to gather all blocks which are spread in the memory into the CPU application, and then we make a single big transition of the total into the FPGA, okay? So you have several collecting times plus one global transfer time. CAPI mode, we make a a first transaction to get the table. We need to get the table to get the addresses. Once we get the addresses, I am the FPGA, so I get at the addresses I've just collected the data myself. All right, so let's see now the results. In traditional way, this is the time we call, so K is a spreading factor. So K is a dispersion factor. If K is 1, all blocks are continuous. If K is 2, the 2 megabytes blocks are spread in twice as much memory. In 4, it's spread in 4 as much memory. So you understand that the 2 meg, either they are grouped, either they are dispersed in a way, either they are more dispersed, either they are more and more dispersed. So it's very basic English, but it's the way I found to explain you. The time for gathering is always the same. That is, time to gather and time to transfer is always the same, whatever you spread or not, more or less. It doesn't depend on the spreading factor. So you collect and then you transfer. Basically, it takes 190 microseconds to transfer 2 megabytes. That's 11 gigabytes per second, which is in the order of magnitude of what we observe with SNAP. So I will introduce SNAP in a minute, but this was not direct usage of CAPI. We were using a little bit of overhead to simplify the user's work with the framework I will introduce. So in this case, whatever you spread or not is the same time. So the sum is basically in the order of 500. Now the CAPI way, they began with Verilog because they were not very happy with the HLS. So they said, in Verilog, we have much better results. Actually, what happens is that we save this time, okay? We do not need to transfer, and this time is reduced because we have direct access. So we collect less, we collect much less, in much less time, the same amount of memory that the CPU does because we have the direct access, okay? And the total is only the figure we have here. With HLS, after my colleague checks what the Chinese team did, he said, hey, you didn't use properly. If I tune that and that and that, then he got even sometimes a little bit better results. This was just for a chance. It was fortunate. Usually with HLS, what we see is that we get almost the same performances, a little bit less, because it's a higher programmation. You can compare HLS with compilation of C, okay? And you can compare HDL, the hardware design language, which defines exactly how you could hook up the gates as assembly, okay? So if you code a real-time routine in assembly, you have chance that you will spend more time, but you will get much better results than if you use a high-level operating system compiled and so on to do the same thing, okay? In this case, it was amazing because at the end, the HLS was much better, a little bit better. So we see that the time has been drastically reduced by a very significant amount going into an FPGA gathering scattered information by itself. CAPI saves the time for the gathering with relatively small penalty when it grows. So at this level, when you increase the spreading, the time is beginning to be equivalent at some time. Oh, sorry, it's better here, okay? But at a certain level, when it's spread, the penalty is a little bit increased. But when it's tuned, HLS can compete with Verilog coding. We'll see that in a minute, what HLS is providing to us. So HLS is a C coding of what we want into the FPGA. Okay? Another example is from a German institute. These guys are postdoctorate or in course of being doctor. And they have made a very simple file system. I think this example is very good of what you can achieve with this kind of acceleration. They wanted to make, remember, there is a card that can store NVMe memory on it, okay? And they wanted to make this card present in the system as if it was a local disk, okay? So they've made, they used a very basic file system to handle the file, but they also wanted to reuse redirection greater than or lower than symbols or characters to be able to manipulate the data instead of just moving them. So the goal was to say you have a very simple string, you equal this string, you pipe to, so black would be executed on host, and blue would be executed on FPGA, while green would be storage in the FPGA. And they wanted to make the user completely, make these operations transparent to the user. You understand what I mean? So you put a string, and you say pipe, I want this string to be converted in uppercase into the FPGA as an action that I have described into the FPGA. So if I ask the FPGA to do the conversion, then I said now I want to encrypt in the FPGA and store in the FPGA. So I encrypt and pipe storage in FPGA. And now if I want to check what is the content of this green located text but decrypted and put in uppercase, I should get a result. So this is what they have made available on CAPI 1. It's working nicely. They use multiple operators to compress, combine, to compress, encrypt, and so on, or filter, or modify the case in a command line, and use the SSD located in the FPGA as if it was a local storage. They use the file system with LMDB, which is an open source, I think, open system. So this is the implementation of their system. They make the file usable through libfuse. They have standing executables inside the FPGA. So inside the FPGA, they have defined different operators. They have an input stream. They select the operator, change case, encryption, decryption, and so on. They offer the possibility for you to put your own operator, and this is the output stream. And the output stream can be stored in the local memory of the FPGA kernel. So that's, I find that this is very funny because, again, I just imagine myself in my lab, and this is the kind of things I'm doing with hardware, and these guys are doing these kind of things in software, just manipulating piece of hardware and making the user completely unaware of what's happening behind the scene. That's really funny. Okay, this is an example. So we, as I said, we put a file and encrypt it with a given key that is located in the FPGA, okay? And we encrypt that into the FPGA SSD, located SSD. We try to decrypt and change the case while re-encrypting after having changed the case into the same file, onto the same message but transformed. Then we try to encrypt with a bad key, and we get garbage because we decrypt with not the same key as we used for encryption. Now we decrypt with a new key, and the message is now recovered perfectly with a change case that has happened in between. That is, there were some capital letters, and now they have disappeared. So it's really a way to show you that we can completely hide the hardware stuff to the end user. And that's, I think it's very amazing. Everything is available on their site. The site was here if you're interested. The site was here. Okay? All right, another example. I don't know what time is it because I can speak for hours. We're almost there? 20? It depends on you. I can stay 15 minutes? Okay. So let's go now to the deeper details. Let's forget about that. Oh, this is the example we discussed with Chim, so we can come back on. I think this is interesting. It's a customer that we are working with. He has a high bandwidth detector. We use InfiniBand to provide the pixels to the it's for synchrotron activity. We provide the pixels to the FPGA. We are working on that today to linearize the pixels which are not linearized. Then we use CAPI 2, or further we will use OpenCAPI to go into the unified memory, so that once an image is completely stored here, we put a flag, and the GPU can access this image, process it, and check if this image is valuable or not, throw it away, and if it's not thrown away and kept, the P9 has a hardware compression capability, which is pretty fast, and we can output the valuable data to the data center. So this is a very good example of manipulating data between an FPGA and this is the details of that, and a GPU inside an AC922-like server, the one I spoke earlier. So let's go into the details of the snap. I have given you lots of the keys. So what brings snap? Snap is a framework, and imagine you are in command of a regular plane, airline, the one I will take tonight to go back to Europe, and I will probably have a captain here, and a co-pilot. In terms of case, the commander is the software captain is preparing the application, and usually you need a hardware co-pilot to write the HDL to describe the logic and how the registers and gates are hooked up, and this requires specific skills and specific experience and requires time. We pretend that we can remove all this control panel, keep the motor, we keep the engine, but I'm a glider pilot, so I just mentioned that in our case we keep the engines. In the glider, we don't have the engines anymore. But we want to simplify and get a very basic using CAPI, we have spoken about that, the framework I will introduce, the HLS, which I have spoken about, conversion from C to HDL, and the power technology. We pretend that we can simplify a lot the fact that you can drive a fast plane. So first choice, you use your application with libcxl, you use CAPI link, you have the blue, remember at the beginning in the Lego stuff, we had the blue at the bottom right side, the blue stuff that we provide now since yesterday is provided to everybody on a given example for the Alpha Data card. So you get that from IBM, and you write your software program and you describe your logic with your copilot, and you are set. With a snap, you have the possibility to have a complete environment and treat all this in, here you are with our snap, so you just use CAPI, and you define your own program, your own logic, and you make your own transfer. You deal with how many packets at a time you want, you deal with your job, you deal everything by yourself, but you have the maximum bandwidth and capability. That's the first choice. You have the complete access to all functions, and you do everything by yourself. Second option, you use Snap. You get all the security features that IBM is providing. You are portable from CAPI 1 to CAPI 2 to OpenCAPI. It's open source. Everything is located here, on this site. And here on this site, you get all the examples I have provided, the scatter gather, you get the other one we will go through in a minute. So the concept is just that every actions that you have in the FPGA, they can talk to the outside world. And because it's an FPGA, you have control direct, as we said, to memory and external world. With CAPI, you have the fast link and the coherency. With Snap, we had an extra layer which handles much more easily the access to local memory and network. And Vivado HLS is from Xilinx. Vivado is a Xilinx tool that they use to program their FPGA and that they provide to us, to the user. We can program, it's optional, but we can program that in C instead of coding in HDL. And this is what is saving us lots of time. This is how we began the presentation with 11 days only required to transfer an incomprehensible SHS3 function that Bruno never took time to understand. He took the function and put that into the FPGA without having the need to code the function by itself. And this is what makes things very interesting today. So if you use a Snap framework, you get the same as before. You have a basic library to talk to the hardware. We had a Snap library to handle queues. We provide a complete framework which allows you to hook up a memory, to hook up an NVMe, to hook up a network. But since it's a Xilinx IP, we cannot make it open, but it's provided by Xilinx. That there are some open software that provides, open hardware that provides link to the network. And through this hardware bus, we just need to program in C, or if we want in RTL, in HDL, the function, and we are set to accelerate our function. So we are not obliged to have things in parallel. The basic standard mode is serial. The software program calls the function does a job and returns an output that is done. But you can also begin a function on Monday morning, and all during the week, as soon as the function gets some interesting video from the net, it uncompresses them, checks if there is activity, and returns the result in memory if the activity is interesting or not. But the program can continue by itself, and the function can continue by itself. And Friday evening, you switch off everything. The function being called by the program, but can live on its own. Okay? You are not tightened to answer the program regularly. We can work in interrupt mode or in pull mode, 2 options. And what we have discussed, and now it goes very easy, the FPGA and all things that are attached to it is seeing the memory as if it was a core. So there is core 1, core 2, core 44, and so on of your P9, and your FPGA sees those memory with the same rights as any core. Okay, I think we won't go through the Hello World example. This example is just to show you how we move a function from the CPU to the FPGA to transfer characters. So if you're interested, we go into the details of the different files. Basically, we have a snap allocation, which is providing the memory to the FPGA. So the FPGA exchange is voluntarily limited to a very little number of registers. We basically provide input address, output address, type of function. If the function is very complex inside the FPGA, we want to provide some instructions to say we want you to do that. But we have limited the number of exchange because most of the valuable content should be located in memory. If you need to exchange flags, for example, saying in my example of capturing an image, I want the FPGA to say the GPU, the image is complete. I will write a flag into the memory, so I don't care about this exchange communication, very low bandwidth communication stream. I will put a flag, hey, image is ready. The CPU checks the flag. Flag is ready. Okay, GPU, your turn. You can process this image. When you're finished, I will inform the FPGA. So the CPU is really acting as a orchestrating, and very little number of instructions are required to make the complete computation process to work. Okay, let's avoid all these details. This is the way we exchange the data. So everything is detailed here to have a good comprehension of what's happening. At the end, you detach the action, you detach the card, and you free the buffer that your application used to converse with the function. So basically, what we expect software engineers or any engineer working with Snap to do, take a complete application, define, as we said in the beginning, what is the action that is a good candidate for acceleration. The first step is to make this run into software. That is, we expect you to isolate the function, put it into a specific standalone software, make sure that this software is not accessing resources that the FPGA might not access. Like, for example, the clock of the system. FPGA cannot access the clock of the system. So in the SHA-3 example, the open source example that was provided made the measurement of its own performance by measuring the clock tick before and after the computation. The goal was to compute as many keys as possible into a given amount of time. We had to reroute a little bit this measuring factor so that the FPGA was not dependent on this time, because the FPGA has no mean to know the system clock. It has no operating system working on it. He only knows how to get data from the memory or to get data from the system he has been attached to, the network or disk, but he has no mean to access any operating system routine. Okay? So make sure you have a function that is standalone. Once it's working in the environment, so you make a simple make sure your function is working fine. Then you can simulate you rewrite your function into HLS, you compile or synthesize with HLS, build a fake behavioral description of your hardware, you enter into a hardware simulator. The hardware simulator will emulate a Power 8 or Power 9 system that you will fakely exchange data through a fake CAPI2 or OpenCAPI link. The system will answer you. You can measure timings and so on of your function. So that's, you can enter into the hardware world if you want, should you need it. And once you have done that, and this is very important because here you really emulate your power system. Once you execute, in 99.5% of the cases, it's working. So this is a SHA-3 example. I won't go through. We just said that we had to remove these clock calls. Anytime we check that we have recursive or parallel loops is very interesting because in hardware, you just need to duplicate the hardware. If you have a loop that is executing like 20 times things that are completely independent in software, you wait for the first one to be finished and you execute sequentially 20 times. In hardware, you just say, hey, parallelize as much as you can. So the more you can parallelize in hardware, the more your acceleration factor goes. This is how you can achieve times 35 acceleration with hardware. This is a comparison with CUDA. Okay, this is you can see how much occupation you have in your FPGA. This is a CAPI 1, a very old FPGA, but you have, with Xilinx tools, you have a mean to know how much the blue stuff is taking and how much so each implementation here is a SHA-3 computation element. In this case, we have 16 of them. In this case, we have 32 of them. It's an old technology, but this is how it could achieve 35 times the computation time. Okay? All right, so I think we have an ecosystem around OpenCAPI itself, and Vivado is a Xilinx provider. OpenPower for sure is running our system. And we have Nimbix with hosting Power 9 systems, CAPI cards, and card providers. Most card providers are here. Some of them are available on Nimbix. It's very low cost. It's only 36 cents per hour to play on the development side. You get license of Xilinx Vivado included. You have an access to the simulator. And if you want to deploy on Power, it's only $3 per hour to deploy on Power. But deployment, when you make a tutorial, is like 5 minutes. Okay? So 3 good reasons to try. It's just 1 hour or 2. And with all we have discussed here, you have already saved 1 hour of work because you have most of the knowledge required to enter that. It's available for anyone who knows C and C++ to program an FPGA. And the investment, if you don't have a Power 9 or Power 8 system in your university, you can play with Nimbix for very low cost. We wanted you to be ready in your mind to isolate your function, be ready to simulate it, and then to play with it on Power. And these are our names if you want to contact us and get in more details. So now the question is, Dr. Panda wanted us to come and see future collaboration could be occurring, or if you need any further tutorial, or if you need access to our machines to make some experiments. Nimbix, they don't have P9 today. By the end of the year, I hope they will have P9 available. For training, you can contact also us because we have machines in Montpellier in France. So you can hook up to the machine. For example, here, I have, I don't know if the link is still open, but it's an OpenVPN link. And it's like few hours to get you access to a machine. So, for example, here it's a P9, okay? Can I enlarge that? No. On this P9, we have okay, hold on 1 second. Let me take the other one. Okay, so here, if I LSPCI and ask for what accelerator did you find in the system? He said he found one, and this was the initial kernel discovery, and he created for me a virtual like port, which is not a PCI Express port, but it's treated like it is organized and sorted in the same area as PCI Express. But this makes sure that I have an acceleration available in CAPI 2 mode. Okay, so I have a small routine that allows me to check what cards I have in my system. So it's a very simple script that checks some directories into the kernel, and I have made a human interface to have a PSL revision. So what's inside, what version I have inside the blue part of the FPGA, what is my device ID, what is sub ID, what is the image like? Is it a factory recovery image, or is it a user image I have stored myself, and so on. And the port I am plugged in, and the physical port. And so I can type a snap maint -v, and he will ask me sudo privileges because I didn't. Okay. So it's in snap software tools, snap maint -v, and it says, okay, in the FPGA you have a snap frame network example, which has an ID of 1014, which is the IBM ID. Number 0 is the basic standard demo HDL written example. And so I can run a test on that. I have an actual binary inside the card. I can program the card. I will not go through them unless you're interested. We can do it offline, but I can reload a new binary that I have prepared for you to take into account. When you have made all your C++ writing and so on, simulation, everything is okay. When you push on the button to create the content of the FPGA, which will be stored in a flash, it takes about 1 or 2 hours. But you really build a chip. A colleague joined us in our team. He said, "My God, 1 hour and a half. That's long time for compilation." I said, "It's not compilation." I said, "You are building a complete chip." "I don't care. It's too long. It's too long." And then 1 month or 2 months later, he came to me and said, "We were working with Peter Hofste. He's working with university. Maybe you know him. He was compiling GCC, and I saw notes exchange between Dr. Hofste and my colleague, and one was saying, "Oh my God, on this system it was very long. It took me 5 hours to compile this GCC." And my colleague replied, "Oh, you're lucky. Mine is very slow. It took me 6 hours." And I said, Just a quick note to my colleague Fabrice: 6 hours to compile GCC, and only 1 and 5 hours to build a chip. My God, that's pretty slow. He said, I have no more comments on how long it takes to build a chip." So it was very funny. So you build a chip into, let's say, 1 or 2 hours. Once you get the binary, we have a tool. Once the card is recognized, we can push the binary inside the memory of the card, and at next power up, the binary of the flash will program the newly function that you want to put in the FPGA. It will be still recognized at CAPI mode, but then the function, your function, will be present and you can play with it. Okay? I'm free for your questions offline because